Okay, let me just explain to you today a little bit of to summarize this concept of integrals, and I will just do little review about the two ways of how Riemann sums are used to define definite integrals. Okay, then I will move. This is the first part. So second part, I will explain the fundamental theorem of calculus. Okay, let me just review how we define Riemann sums. So the idea of Riemann sums is to be able to come to an approximation of the surface area under curve. Basically, this surface area, as you can see, this one, see? That's the exact surface area under curve. What Riemann did, he take a subdivision of certain number of intervals. For instance, here I have 4 equally spaced labels, 1/4, 2/4, 3/4, 4/4, okay? So how you label them 0, 1, 4, 2, 4, 3, 4, 4/4. Then the easy case is just to take either left end point or right end point, and I'm gonna explain. That's actually Riemann who did that. So what he did, like for instance, if I take subdivision has 0, 1, 4, 2, 4, 3, 4, all the way to 4/4, okay? So now I can pick any point here. If we pick in particular a right end point, so I can see if I go all the way to the curve with the right end points, I can make up some rectangles. See these rectangles, and here is the first one. I'm gonna just first one all the way with this blue thing, actually, who has the surface area 1/4 times the height is the function, okay? So like for instance, the height here is f of 1/4. So this is the first rectangle. 1/4 f 1/4. Now second one is 1/4 times f of 2/4, this one. Third one, which is actually this one. Okay, third one is this one. Okay, it will be 1/4 times f of 3/4. Okay, the fourth one, it will be 1/4 times f of 4/4. You can see that the height here, like f of 1, this is f of 3/4, etc. This is f of 2/4. Okay, and subdivision actually is x naught, x naught. Okay, and the distance between them is they are equally spaced. This is delta x, you can see, is 1/4. Anyway, Now, what we do, we increase the number of subdivision. And if we increase the number of subdivision, this is what will happen. Actually, it will cut off this one in half. If you take 1/8, what will happen? You go all the way to here and you cut here. Sorry, you go like this. You will cut here. This is the first one. Second one, then you divide again this one like this. Then you only have this one and this one. This one, it will be, it's pretty much like cutting. Okay, you will only have this one, then etc. If you take 1/16, you will again cut this one in half, etc. Then it will be much better. Actually, we remove this one. I will get just this one, and this one it will go to 0. Let me just give you the picture. Okay, if you take 1/n, 2/n, 3/n, 5/n, n-1/n, all the way to n/n. So if you take right hand points, it will be this. Okay, this is one. Then this. Okay. And the general one is this one actually. So now last one will be this one. Now, if you compute surface area of this one, we will get a function of n, like for instance, the one I use with n equals 4. Now just imagine I give you this one with n. N can be any number, and that's the good thing. So now if I take this one, this is 1/n. Okay, all this, the width is 1/n. So what will I get? I will get the first one will be, and this is f of 1/n. It will be the first one. This one will be 1/n, f of 1/n. Okay, this one. Second one, this rectangle will be 1/n, f of 2/n. This one will be 1/n, f of, this is f of 3/n. See? Now, if I go to this one, it will be 1/n, f of I/n. So if I go all the way to this one, it will be 1/n, f of n/n, which is f of 1 in this case. I'm just giving you an example. Now, if it's surface area, you just add them up. Okay. What do we get here? We will get 1/n. You can see that there is 1/n. So if I want an approximation in general, 1/n f of 1/n plus 1/n f of 2/n. That's what we will get, okay? And you can see there is 1/n is like sum. This is if you want to use the sum 1/n f of I/n. Okay, which is I goes from 1 to n. That's really what I'm trying to convey. So now this one, if n goes to infinity, again, as I mentioned before, we will keep cutting this one. This one, this leftover will go to 0. So because if you just imagine you divide by 2, this one, look what happened here if I divide. Okay, this one will go away. Okay, this one, delete. Okay, that means it gets smaller and smaller. the leftover. Then if n goes to infinity and becomes very large, so this one will go to 0. And that's exactly what we call definite integral. So, and we can do this one with left-hand points. You can do it with this one, see? Now, if you pick left-hand point, this one and this one, and this one, and this one, it will be under. So, see, it will be under. That's for 4, okay? So it will be, so the leftover is here now. Now, if you do 1 over 8, what happened? This one will becomes less because you will cut this one into, now when you go here, you will get this one, see? So this one will become less and less. You are getting less than, if you increase, and again, you will get there. But it just the sign is different, but you will still get the same integral. This one will be 1 over n sum of I over n, but you will go all the way to n minus 1. That's the only difference. Okay, so in general, actually, if you want, you take the midpoint, it will be here. But in general, you can take any point here, any point in between. Doesn't matter. You can take anyone here, okay? Now, when you go, the height will be this, and that's the rectangle, see? This is C1, C2. This Ci can be any point between xi minus 1 and xi. Now, if you do the same 1 over n f of c1, if you take this sum all the way to 1 over n f of cn, this one will give you still surface area under curve. Okay, and that's what we call definite integral. Now, if you want to know what is definite integral, this is exactly what I just say, integral from a to b, f of x dx will be limit as n goes to infinity of sum of f of ci I from 1 to n. You take any sum, but you take n goes to infinity. And obviously this gives you if you have a and b, this definitely gives you the surface area under curve. This is how we define the definite integral. So this one is the same as this area. And that's what Riemann did. I think this was a Riemann idea. We used Riemann sums to find this one. Now let me show you a big investment is what we call, but this one is very hard. So using are cumbersome. Just imagine if I give you, well, find surface area under curve of sine x from 0 to pi, okay, using Riemann sum. You will get some crazy stuff, okay? You will get something definitely crazy. You have to deal with some series pi over n sine of a pi over n or k pi over n like this. Then limit as n goes to infinity. That's the area. It's okay. It's an approximation, but this one is extremely hard to compute. Okay, but the Riemann sum are linear. We can still show very interesting properties of integrals like linearity, and we can conclude still like some properties like integral. This one is same as f of x plus integral of g of x dx. Okay, it's linear, so it preserves. This is the summary. Okay, or difference. It could be actually the difference. You can have minus f of x minus g of x. You can actually prove that integral from a to a of f of x. Just there, that means there is no area from a to a. See, if you have a curve from a to a, just zero. You can prove integral from a to b. Okay, and you can prove many linear properties, but these are properties, but doesn't really, it's not practical to compute surface area. If I give you, it's still a very hard problem. Okay, this is what happened. There is, I think, some Leibniz, Riemann, Newton. I think if we combine the work of Leibniz, Newton, and some other mathematician, we can, there is very nice theorem. Actually, this is the fundamental theorem of calculus. Okay, FTC. This is the most important theorem in calculus. In other words, this is the most important theorem in calculus. I mean, if you look to the history of calculus, this is what is telling you. Actually, since Riemann sum are okay to is actually give very, very good approximation, but doesn't give the exact value. And even if we try to use this Riemann sum is extremely hard. Now, look what happened. Now, if I take, for instance, this is what is telling you. If f has nice properties, f, of course, is continuous on some interval AB, closed interval. Okay, and it has derivative differentiable. Okay, just continuous actually. And then the integral from a to b of f of x dx Okay, this is, let's say I'm gonna think of the function as positive or non-negative, not non-negative. Okay, so this one, look, the magic of this theorem is telling you, you just take an antiderivative. You remember the antiderivative of b minus f of a. Magic. Very beautiful theorem. I don't know if you can see. This theorem is a really very nice shortcut. Okay, and f is just an antiderivative. Okay, so let me give you an example of this one. Let's say this is cosine x, f will be sine x. So it will be, let's say I'm integrating cosine from 0, say, to pi over 2. Then I will get sine of pi over 2 minus sine of 0. It will be just 1. But if you try to do it with Riemann sums, good luck. It is very hard. Let me give you an example. So this leads us to say that if you have a function, let me give you first an example. Just take y equals x squared, or f of x is x squared, okay? And I want to see, I ask you, what is surface area under curve? This is very easy. It's very easy to see that surface area under curve is this one, okay? Well, if we can still use Riemann sum to solve this problem. This is still okay, I think, with Riemann sums. We can still find A is 1/3, if you remember. With Fundamental Theorem of Calculus, let's see what we will get. So I will get the area is integral from 0 to 1. Okay. Now I need to figure out what is an integral of x squared. This is x2 plus 1 over 2 plus 1. Okay. That's the antiderivative, which is x from 0. This is how we will write it down. And by the way, here from 0 to 1, which is so an antiderivative of this function is this one. Now you just plug in 1 cubed over 3 minus 0 cubed over 3 is 1/3 minus 0. So that's exactly 1/3. Okay. So this one is very neat shortcut. That's really, now let me give you some little bit more difficult. Just imagine I want to look for the surface area of cosine. Okay, this is cosine x. Okay, and I want surface area of this one. Just imagine if you want to use Riemann sum. You have to take subdivision. You have to compute sum, actually this sums of this rectangle. It Riemann sum is inconclusive. It will be extremely hard. And Riemann sum is just impossible. Now, if you want the area, you do just from 0 to pi 2 of cosine x dx. Okay, what is an antiderivative of cosine x? So, antiderivative is sine x. So this is what we're gonna denote f of x, okay? And this is actually f of x, lowercase. So now if you compute this thing, it will tell you sine of x between 0 and pi over 2. And what is the meaning of this? This means is sine of pi over 2 minus sine of 0, which is 1 minus 0, which is 1. Okay, so this area, can you imagine, is exactly 1 unit square. Very nice for engineers. So if you have a function, you want to compute surface area under curve, the fundamental theorem is very, very nice theorem actually that you can apply. But here you have to be careful. The integral is not always surface area under curve. You have to assume, so we must assume some. So the area under curve is integral from is non-negative. So it has to be over the x-axis. If it's not, then it's a problem. It's not surface area. It's algebraic surface area. Then this one will be the exact surface area under curve. Now, if you want algebraic, what we call surface area, if you have a function like this, can you imagine I give you a function like this? Then you have really to be careful. It can be 0. So, but when you do, if this is A and this is B, what you will get? This is positive. It will cancel out with this is negative. So you have to be careful. Okay. And namely, if you have something like this, like, for instance, which function could be this one? Pi, negative pi. See, if you take integral of minus pi to pi of sine x, this one will be 0. But it's not surface area under curve. It's the algebraic surface area. Because this will be, if you do the math, this is like minus cosine x from minus pi to pi. Okay, it will be 1 minus is 1 minus 1, which is 0. Okay, this is actually, if we take this one, will be cosine from 0 to pi, minus cosine from 0 to pi is minus cosine of pi minus cosine of 0. Yeah, this is actually cosine of pi is same of this will give you 0. Okay, anyway, the point I was thinking about here is just you have to be careful. It's not surface area and the curve, but you just look if it's this. This will be interesting because you can compute the surface area. Is it the exact surface area and the curve? If they alternate, you will have the algebraic surface area. Okay, let me just give you some examples just to finish. One, let's say if I want to give you integral from 0 to 1, okay, so here I need to use the power rule. Remember, power rule is telling me I always tell my students of Calc 1, this is the most important probably rule for integrals and derivatives also. There is one. Okay, here there is no bound. Actually, that's the power rule. Okay. Now here n is 2, then you will get x cubed over 3. Here is 1, it will be x1 plus 1. And here it will be just x from 0 to 1. Okay, now if I do the math, this is f of x. Here, remember, f of x. Okay, what is the fundamental theorem of calculus telling me? Will be f of 1 minus f of 0. And what is f? It's just an antiderivative. So this is one antiderivative, okay? I don't know about sign here, but here I'm not looking for any surface area, but here I'm just computing for you. And if you do 0, it will give you just 0. F of 0 is 0. So then, anyway, then you can just compute this one. It will be 1/3 minus plus 1. Okay. If you multiply by 3, it will get you 2 over 6 minus 3 over 6 plus 1 is 1 minus 1 over 6, which is, it looks like 5 over 6 if I didn't make any mistake. Okay, so let me give you a different one. So if I give you integral from 5 of 1 over x dx, so we have to figure out what is an antiderivative. So you can just compute this one, which is logarithm, okay? Yeah, I'm gonna assume x is positive here, so we don't have to worry about the absolute value. So now what this is telling me, if this is like surface area under curve is the same as the integral. Why? Because if you try to compute from 1 to 5, you can see clearly that surface area under curve is this one. But if you want to use Riemann sum again, it may not be easy to find surface area. But with this fundamental theorem of calculus, what does it tell you? This is the antiderivative. It will be just ln of 5 minus ln of 1. And what is ln of 1 is 0. It will be just ln of 5. So you have, that means the surface area will be ln of 5. So just be careful when it's surface area and it's not. So let me give you a third example. So if I give you this function integral from minus pi to pi of cosine x dx, for instance. Okay, if I draw the cosine, it will be 0 pi over 2 pi. And this is pi over 2, of course. Now if you do the matching, okay, you can see clearly that this one is positive. So if I go from negative pi over 2 to pi over 2, it's just surface area, but these are negative. So I will get here, do I get an algebraic or the exact? Here I will get the exact surface area. Now what is one antiderivative here? It will be just sine x, okay? So now it will be sine of pi minus sine of minus pi, which is the same. This is 0 minus 0, which is, and you can see why, because this one is the same as this one in terms of area, and this one is the same, but they cancel each other. So that's why. So the algebraic surface area, you can say, is 0. Thank you very much. And that's close this chapter, okay? Thank you. Oh, I recorded, I thought.